Hi and welcome to this webinar about CFD mesh controls in LS-DYNA. My name is Marcus Timgren and I'm working at DYNAmore Nordic. And if you have any questions, please send me an email. Today we will talk about CFD mesh controls in LS-DYNA, and I will start with an intro to the automatic mesher. And then I will explain a user-defined mesh, and after that I will explain the boundary layer options and different control cards that you can use to control the mesh. And after that I will explain how you refine the mesh locally, and last I will explain how remeshing works. The solver has an automatic volume measure with an option to create the boundary layers. So as a user, you input the surface mesh of your fluid volume, but it's also possible to create a user-defined fluid volume mesh if you want. In order to use the automatic measure for a 2D case, you have to mesh your boundary mesh with beam elements, and for a 3D case you have to mesh the boundary surface with triangles. And when you have done that, you have to convert the general LS-DYNA format from star node to star mesh surface node and star element underscore shell to star mesh underscore surface underscore element. And you can do this with LS-Prepost or with a text editor. In LS-Prepost you click on mesh and then MS mesh and select the whole model and press convert. And in order for the automatic measure to work, you cannot have duplicated nodes, since the solver does not allow to have two nodes in the same location. And you have to have a watertight volume, which means that you can't have small gaps in the model between two surfaces. And for each boundary condition you should have one unique part ID. So for example, in this model here we'll have 5 different boundary conditions. The inlet has part 1, the outlet has part 2, and the main walls here has part 3, and the ground has part 4, and the plate has part number 5. The keyword mesh underscore volume defines which surface part that the solver will use when it's creating the volume mesh. And only one volume is supported with the automatic measure. So with this keyword you select all the surrounding surface parts and then press insert and then accept. So this will create a fluid volume between part 1 to 4. If you instead will use a user-defined mesh, and the ICFD solver only support tetrahedral elements in 3D and triangle elements in 2D. And you can download a basic example from dynaexamples.com that shows how to set up a user-defined mesh. And I will go through it a little bit, the steps that you have to take to use a user-defined mesh. So when you have created a mesh, you have to convert it to from a general LS-DYNA format to a ICFD format. And you have to modify the mesh keywords manually for the fluid volume mesh. The automatic way in LS-Prepost does not support a 3D mesh, it only supports surface meshes. So you have to modify the star node to mesh underscore node or the old keyword mesh underscore volume node underscore node, and your element solid to mesh underscore volume underscore element. One important thing for solid is that you can't use the 10 noded format at the moment, so only use a 8 noded format for your solid mesh. And for the boundary conditions, you have to use set node list. So you should define, before you convert it to the mesh to a ICFD format, you should define your set nodes and then convert them to ICFD set node underscore list when you modify the mesh. So here on the left side is the structural format that when you create them in LS prepost, and on the right side we have the ICFD format. So you only change the heading and the second line, the rest is the same. So here you have set ID 1, which is the same for the ICFD, but the second parameter is the part ID that the ICFD solver will use. So same thing for set node ID 2. You keep the same set ID here and convert and tells the solver that this will be part number 2. And same thing for the rest of the boundary parts. But you can have a different part ID than the set ID. I have just used the same, but you can have, for example, 10 here if you want. Apart from these steps, you can define your case as usual, but you don't have to use mesh underscore volume, since you already have created the mesh. And a 3D case is defined in a similar way. It's no difference between a 2D and a 3D case. The only difference is the element formulation, that you use tetrahedral elements in 3D and triangular elements in 2D. And no remesh is supported for a user-defined mesh. Now over to different ways of controlling the automatic measure, and we will start with the boundary layer options. So to create boundary layer, you use mesh underscore BL, and mesh underscore BL underscore sim is often used as well. What mesh underscore BL underscore sim does is that it tells the solver to propagate the last elements out to a certain boundary. So for example, here you can see a case when mesh underscore BL underscore sim has not been used, and as you can see, the last boundary layer is squeezed down to the last node. But if you use this keyword, the boundary layer will propagate with the same direction out to that boundary. And this keyword is used at domain boundaries that doesn't have a boundary layer mesh. You can control the boundary layer option on the keyword mesh underscore BL. And the first parameter is the PID, which controls from which part the boundary layer will grow. Then you have the NELF parameter, which controls the number of nodes in the boundary layer. And then you have a parameter for the boundary layer thickness, and then a parameter for the distance between the wall and the first node. And then you have a parameter that controls the method that is used when creating the boundary layer. And in R9 you have 3 different methods: the default method, 0 that only uses the parameter NELF, option number 1 which uses NELF and the parameter BLTH, and option 2 that uses all parameters. And here is an example that shows the difference between the methods. In all examples I have used NELF equals to 3, which means that we will have 3 nodes in the boundary layer. So for example here 1, 2, 3, but we will get 1, 2, 3, 4 elements. And for options 1 and 2, a boundary layer thickness of 0.05 was used. So with the default method 0, the solver creates a boundary layer based on the surface mesh size. So the only thing you can control is the number of nodes in the boundary layer. With option number 1, you can specify the thickness of the boundary layer and also the number of nodes in the boundary layer. And with option 2, you can control both the thickness, the height of the first node, and the number of nodes in the boundary layer. Now over to the control cards that affect the mesh size of the simulation. And the keyword ICFD control underscore mesh has an option for a mesh growth scale factor, which determines the maximum mesh size based on the surface element size. And this factor can be between 1 and 2. So if you set the growth factor to 1, you will have the same size as you have on the surfaces in the fluid volume. And if you set it to 2, you will have twice as big elements in the volume as you have in the fluid on the fluid surfaces. And the next option is mstrat parameter, which controls the method that is used when the mesh is created. And the default option is the DYNAmore criteria, and the other option is an octatree method. And for 2D cases, you have an option to create structured or unstructured mesh, and the default is unstructured mesh. If you want to refine the mesh locally, you can use mesh size and mesh size shape. With mesh size, you use a user-defined part to define the level of refinement, and the part has to have a mesh in a ICFD mesh format, and inside that part the solver will use the mesh size that is generated on that part. And it's possible to use more than one part in a simulation. So what you do is that you specify the volume ID that is set on the mesh volume keyword, and then you create that part that you want to use, and don't include that part in the mesh underscore volume keyword, only include it here, and then press insert and accept. So if you want to test this, you have an example of this at DYNAexample called basics mesh size example, and here is the input. So here is the refinement part, and this is what the solver generates. So you can clearly see the refinement here inside the box. Another way to do the same thing is by using mesh size shape. This keyword uses predefined regions, and you can use a box, cylinder or a sphere. And you define the coordinates for the specific shape and also the mesh size. So here is an example how the keyword looks like. So here you choose the shape that you want, and this parameter controls if you should keep the refinement after a remesh occurs. And here you enter the mesh size that you want inside the box in this case, and then you enter the coordinates, the minimum coordinates and the maximum coordinates in each direction. To demonstrate this, you can use the previous used example, but you have to modify it. So comment the include mesh size.key and uncomment the mesh _size _shape keyword. And then you rerun the case, and if you view the mesh, you can see small difference in the boundary where the refinement occurs. It's not as sharp as it is with the mesh size keyword, but otherwise you get this pretty much the same mesh. Regarding remeshing, so is the remesh is always on if an element inverts, but you can also activate it if the mesh quality deteriorates. So use ICFD control adapt size and set the A size parameter to 1, and the NIT parameter controls the number of iterations before a remesh is forced. And I recommend to use a high value, since a remesh should only occur if needed. And since the remesh or the meshing only uses one CPU, for big models you can slow down your simulation time if you have a low value here. It's also possible to use adaptive remeshing with the keyword ICFD control adapt, and the new mesh is computed based on a posterior error estimator that will satisfy a maximum percentile global error that you as a user specify, which is the parameter ARR here. So this means that you allow 2% error estimator. And you also specify the minimum element size and the maximum element size. And the MTH parameter here controls if the error should be based on function or gradient. And the NIT parameter is the same as the previous keyword. It controls how often the remesh is forced. And I do not recommend to use this keyword since you can slow down your simulation, so only use it if needed. You can download an example with adaptive remeshing on dynaexamples.com, and the example is called, it's located under basics and it's called mesh adaptivity. So here you can see how the mesh changes during the simulation. That was all for this webinar. Thank you for listening, and please send an email to my email address marcus.timgren@dynamore.se if you have any questions. and subscribe to the YouTube channel if you want to stay updated on when the next webinar is available. So thank you and have a great day.